This topic is given by Professor Zhenbin Yang from Tsinghua University. It's going to talk about quantum channel capacity of transversal wormholes. Okay, let's begin.
Okay, thank you, Wenqiang. First of all, I would like to thank the organizers, especially Professor Yao for this kind of invitation. Actually, last week is my first time to visit Huairou, not to mention Binsan, and I'm really impressed by this beautiful scene and very pleasant weather here. So also, I think the conference went very well last week, so congratulations. Today I'm going to, I'm seeing that it's a very broad audience, so I thought about what I'm going to talk about. So I think this subject probably have a broader interest compared to my, nowadays my main research focus is about firewall problem. So this work is a work in progress with two of my students, both at the Institute for Advanced Study at Tsinghua University. One is an undergrad student, Zhenbin Yang, and another is a grad student, Lu Jinru. The work is trying to do more kind of a systematic study of the Gauss-Jeffreys wall traversable wormhole protocol from a quantum information perspective. More precisely, we're trying to analyze its something called quantum channel capacity, namely view the traversable wormhole as a quantum channel and ask how big quantum information rate it can send through the wormhole. So please stop me at any point if when you have any questions. I think this subject may be unfamiliar to most of you, so I welcome questions. So first of all, let's have just a lightning review of the Gauss-Jeffreys wall traversable wormhole protocol. So let's first consider the standard Panel's diagram of two-sided black hole in an anti-de Sitter space. So it's a ADS structural black hole with an asymptotic ADS boundary. So it's a time-like boundary. So one important feature about this Panel's diagram is that light goes 45 degrees. So this Panel's diagram preserves the causal structure of the space-time. Another important feature of this Panel's diagram is that it has both left boundary and right boundary. Left boundary and right boundary. And these two boundaries cannot talk to each other. So the time runs from -infinity to +infinity on the left boundary between the lower corner to the upper corner. And the right side time runs from -infinity to +infinity here. And you can see that they are causally disconnected because of the horizon represented by this dashed line. This horizon represents the both the future and past horizon of the structural black hole. And because we have two asymptotic boundaries, the left and right, it describes a geometry that connects connected geometry connects two black holes. So in other words, it's an Einstein-Rosen bridge, or usually called the wormhole geometry, connecting two black hole systems. So if we think of in terms of ADS-CFT or more generally in the context of holography, this left boundary and right boundary represent the degree freedom of a quantum mechanics system. So this Panel's diagram describes a geometry that is due to an entangled state between the left side and the right hand side. And the horizon ensures that for an entangled state, you cannot transfer information between each other. So for example, if you do a local unitary on the right-hand side, the signal cannot transfer to another side because of the protection from the black hole horizon. So that is inconsistent with the idea that if there are two entangled states, then any local unitary on one part of the system cannot change the state of another side. Okay. So sometimes I'll write the state as a sum of your double state, and for that, in particular, I mean a state that is corresponding to a state at the t equal to 0 side. So t left equal to 0 and t right equal to 0, and both time run to the upwards. So that's a state where the distance or the volume of the wormhole is the shortest connecting the two sides, and we usually think of the state as being the simplest state. And then you can see that this geometry under time evolution have a rapid evolution because the volume of this Einstein-Rosen bridge is keep growing. So it's a very time-dependent geometry. Okay, another feature about this geometry is that it has a boost symmetry, and that fact is useful in the later discussion. So for example, the boost symmetry consists of so you have a boost symmetry, and it consists of moving the right time upwards and the left time downwards. So that's generates a boost symmetry. In terms of Hamiltonian, it's h right minus h left, and that's the symmetry of the state. The sum of your double state is invariant under the transformation of the boost. Okay. So far, any questions? So that's just a basic review of the maximal extended structural background, structural geometry in the ADS background. Okay. So because as I said, any signal in this geometry cannot transfer from the right-hand side to the left-hand side because of the horizon. So usually those wormholes are non-shieldable. And as the name suggested, in a work done by Jeffers Wall, they provide a mechanism that can allow a signal to transfer to the other side by doing some kind of a non-conventional procedure. So what do they do is the following. So they consider this geometry and sending a signal from the right-hand side at some early time, t right. And then they consider at a later time to do couple the two-side system and do a double trace deformation. So this is a blue line corresponding to a coupling e to the ig v, where the operator v is a two-sided operator, and it usually corresponds to a operator O left times O right. So it's a two-sided operator. In Handy theory, usually in the context of ADS-CFT, we usually call it a double trace deformation because each operator represents a single trace for the gauging invariance. So it's a double trace deformation. And then there's a coupling constant G corresponding to the strength of this deformation. And what Gall and Jeffers Wall pointed out that because of this non-local coupling, in the bulk, this coupling will generate null energy around the horizon. And more particularly, so let's call this direction as x minus, and this direction as x plus. This null energy will this two-sided coupling will generate a null energy whose sign depends on G. So In this case, it's a t minus minus, will be proportional to g times some vector function at x minus. Okay, and the strength of this non-energy is linearly proportional to the coupling constant g. So by tuning the g as it have positive sign or negative sign, we can generate a negative non-energy condition around the horizon. And then you can use using Einstein equation to solve the back-reactive geometry coming from this negative non-energy. And what you find is that if it has a negative non-energy, then the signal can transfer to the other side. So, and that makes the wormhole become traversable. So some of you may have heard what's called the Gauss-Wall theorem. Basically, it's a different Gauss, by the way. The Gauss-Wall theorem in GR, it tells you that if you have a matter satisfy the average non-energy condition, T minus 1 bigger than or equal to 0, then tells you there's no signaling from the right-hand side to the left-hand side. And what Gauss-Jeffreys Wall pointed out that if you allow to do this double trace deformation, then you can violate this average non-energy condition, and then therefore leads to a signal transfer between the two sides. So that's the main idea behind this traversable wormhole protocol. Are there any questions at this point? Of course, quantum mechanically, it also does not violate the law of quantum mechanics because this two-side coupling, it's a unitary acting on the two sides, and generically a unitary acting on two sides can be viewed as can transfer information between each other. Okay. So what's so interesting about the traversable wormhole protocol and why I'm talking about it? So there's quite a few interesting aspects of this wormhole protocol. So the first and the most important thing about this is that, of course, the signal goes through the wormhole. In particular, the black hole interior. Okay. So in other words, it's some kind of an interior observer that allows you to explore a little bit what it is, the geometry behind the black hole horizon. So those are the quantities that you were not able to observe by looking at the one-side observables. So for example, you can look at 2-pi function only on the one side and calculate the black hole quasi-normal modes or other type of quantities, but those only explore the geometry outside of the black hole horizon. But this traversable wormhole protocol that allows the signal to transfer through the black hole interior. So in particular, it will allow, by reading out the state transferring to the other side, it allows you to tell whether the signal scatters with some other particle behind the horizon or not. And that's kind of useful information to know. And more generally, it's very hard to construct any kind of operator that can probe behind the black hole interior. Okay. The second is from a quantum mechanics point of view. From a quantum mechanics point of view, what we are doing. So we you should think about the left system and the right system. They're initially in an entangled state. And then what we are doing for this double trace deformation, you can view it as doing a kind of a quantum teleportation. We can use this operator as first measuring the eigenvalue of the operator on the right, and then depends on its eigenvalue, we do a unitary on the left system. So we can do it or left depends on the eigenvalue what you measured from the right hand side. So in other words, this you can view this as you can implement this double trace deformation as doing a measurement and a classical communication. So it's a type of quantum teleportation. And in general, it's a bit kind of a philosophical challenge to understand how information transferred during quantum teleportation. So, for example, when you have another qubit that sends through this first couple with the right and then sends through quantum teleportation to arrive to the left, it's mysterious. It's kind of mysterious to ask when the information got transferred from right-hand side to the left-hand side. And and when you learn quantum mechanics, that's one of the main philosophical issues to associate with teleportation. But this wormhole picture gives you a geometric picture for quantum teleportation. It provides an answer for how does the information got transferred from one side to another. It suggests the picture that whenever you have an entanglement between two systems, you can view it as a wormhole connecting between the two sides. And the teleportation procedure corresponding to information goes through the wormhole and goes to another side. And this feature of a wormhole connecting two sides, of course, doesn't depend on the locality of these two systems. No matter how far they are separated, this qubit still doesn't care. It just goes through the wormhole. And that fits quite nicely with the feature of quantum teleportation. And more generally, this idea that the entanglement described by a wormhole is called DI equal to DPR. Yeah. This two sides, right? So there's all left and all right. Okay, so regarding your first question, and it's a very good question, and I was hoping someone to ask so I can explain more. So what we are doing is we have some state that both on the left and right, and we're acting with unitary, and we only look at the system on the left-hand side. So if we only look at system on the left-hand side, we trace out to the right, then it doesn't matter we do this double trace deformation, or we first measure the right and do the unitary. So this is equivalent as we do a projection on the eigenvalue on the right, right? So that's right. Do a projection right. That. And so this projection corresponding to measure the eigenvalue of O. Does that answer your question? Straight answer. Sum of the Yeah, I'm finishing. Yeah, right. This one-side unitary depends on the value of right arm. Yeah. The important thing is that the signal coming out to the right. So whatever you do on the right-hand side after you do this deformation doesn't matter. So it's conceptually which is quantum interpretation, but it's a many-body system. So you will see a much richer structure than the conventional quantum interpretation. It's called quantum many-body interpretation. It's a teleportation protocol that requires you have a many-body degree of freedom. So related to one feature of this many-body teleportation is that some peculiar feature of this protocol is that so basically any operator works for the any operator for the double trace deformation works as a can support a negative stress tensor, and that's because in GR the gravitational force is universal, and so you should really think about the dual quantum mechanics system is a larger quantum mechanics system that have a many degree of freedom entangled between each other, and this teleportation protocol is telling you that no matter which qubit you are measuring, as long as it's inside the system, so O could be any operator, quality operator on any qubit on the right hand side. So you can measure any the eigenvalue of any quality qubit on the right hand side and do a unitary transformation on the left hand side. This allows you to teleportate your initial information. And that this feature that from a quantum mechanics point of view, any operator can work is due to something called scrambling. Okay. So here I'm thinking about the thing quantum mechanics point of view. So in quantum mechanics viewpoint, let's use the Heisenberg picture. So we have a state at thermal field double state at t equals 0, and we are trying to send some information by evolving the system backwards and applying a local unitary and evolving forwards. So the operator corresponding, let's say, denote the signal as phi. So our operator in a Heisenberg picture is coming from conjugating a local operator by a many-body Hamiltonian. Here the H represents the Hamiltonian that is due to the describe the dynamics of the evolution of the black hole, and in the boundary dual it's a many-body Hamiltonian. So in generically, the Hamiltonian is a chaotic Hamiltonian. So that will that will spread the scramble the size of the operator. So for example, at later time, the phi could be a sum of product of operators. O could be many of O. A, then there's a coefficient C. T, sum of K, the choices could be, there could be different species. Yeah. O, yeah, okay, so O means polymatrices, for example. So you have so you can think about there's for example, n spins, okay, and then O means parametric design spin. And we have first the Hamiltonian couples all the spins. It's an auto coupling. And then we have some local operator first acts on the first spin, and under the Heisenberg evolution, this operator can spread over the whole system. So if you like, if you draw a tree-like diagram, then you have some. Each step, this operator gets spread to larger and larger operators. So, so this procedure called the operator scrambling. Okay, and the idea that if you first acting on this local operator that's sending some signal, because of time evolution, this information is scrambled into a bigger and bigger size. So when it spreads almost to all your system size, then any local operations can affect where the information is. And this box diagram is precisely tells you how does the information relocated under some simple simple operation. So so this is related is that this in order for this to work, this time separation between the phi operator and the O operator has to take something called scrambling time, log 1 over g Newton. It's log n. Yeah, sorry. In gravity, because of the Bekenstein-Hawking entropy, the n, the degree of freedom, is proportional to inverse Newton coupling constant. And the last thing I would mention, but not able to explain it, is that this is related to a quantum information protocol called the hidden crystal protocol. That's for S0. But I encourage you to have a look at it. Okay, so that's the motivation part, and I want to pause for a second to ask: are there any questions? Yeah. Yeah, by the signal I want to send. The double choose deformation, right? The separation. Yeah. Okay. Okay. And maybe I'll not. Maybe I'll not explain here. So we want to ask. So the question we want to ask is quantitatively how well the traversable wormhole works. As I said, for example, from point D, in order for the signal to able to transfer from the right-hand side to the other side, there's a time separation between the signal and the double tree deformations. It's a scrambling time. But how precisely the relation is? In other words, how does this wormhole protocol works depends on when we send the signal. So we want to have a quantitative discussion about how well a quantum channel works. And this is characterized by something called quantum channel capacity. We want to have a quantitative discussion about how well this wormhole channel works. For that, we view it as a quantum channel, and we want to calculate information quantity of the quantum channel. So how generally is a quantum channel capacity defined? So let's consider we have a system A that may entangle. We can always purify a system with a reference system. Okay, so combined, we have A union reference system. It's a pure state. And in general, if we have a quantum channel and it maps to an outboard, which is system B, we want to characterize how well this channel works. In other words, that is equivalent as asking how much entanglement is remained between the reference and the B. Okay, and to do that, when we first let's do a rewriting of this diagram. So whenever you have a quantum channel, you can do a dilation, or just like expand it, enlarge it to view it as a unitary and trace out some environment. So you can always do a dilation of a quantum channel to expand to view it as a big unitary acting on a bigger system, and then you trace out some environment systems that give you a quantum channel that only maps to B. Then, in general, when under such a unitary, because combined the reference B and E is a pure state, there could be some entanglement between the reference and B and the reference and the environment, or there could be entanglement between B and the environment. And in order to accurately characterize the entanglement between B and the reference, you can use something called the coherent information. So the coherent information as reference to B is given by the von Neumann entropy of the system B minus the von Neumann entropy of the environment. Okay, and the coherent information is closely related to the quantum channel capacity of this channel, and that is actually there's a theorem in quantum information theory called the Lloyd-Shor-Debtuck theorem. Tells you that the quantum channel capacity of the channel N, which characterizes how fast, how big a rate of quantum information can send through the channel, is given by the maximum of the coherent information to B, and maximize over all your initial states, and not precisely, and you need to do some kind of a regularization of the coherent information. So the regularization is, so let me write it some math formula, and I'll explain what this regularization means. So it roughly tells you the channel capacity gives you the maximum coherent information, but in a regularized version. So what does this regularization mean? It means instead of consider one copy, let's consider n copy of the system. And then we maximize all the initial states among these n copies. It does not necessarily to be a product state, and in general it's not. And we calculate the channel capacity in this replica system, and then divide it by n. And then take the limit of n goes to infinity. And by doing that, this maximum of coherent information give you the channel quantum channel capacity of the channel. Okay. And from this definition, it's also clear that if you only have one copy, that serves as a lower bound of this channel capacity, and usually we call the one-shot channel capacity. Okay. Any question at this point? So if not, then we will discuss how to use this LSP theorem to yeah. Yeah, the unit of U and then trace out E. Yeah. So you start with first with a channel N that maps from A to B. Okay, then you can always extend this N to a big unitary and trace out the system E. Yeah, this channel can be recovered by tracing out the E of the E. Mm-hmm. This E is arbitrary, arbitrary such that after you trace out U, U it gives you the original cross operator. But there's certain ambiguity. So, for example, you can do a general unitary rotation of the E, but that doesn't affect the coherent information. Does not affect the channel capacity, quantum channel capacity. This one? Yeah, that's right. And the good thing, well, maybe if you want some intuition, I think it's not rigorous, is the following. So thinking about this reference, it has an entanglement with E, entanglement with B, and B has an entanglement with E. Okay. So first, the most naive thing you calculate how the reference and B are entangled, you will calculate the von Neumann entropy of B. But that's not good enough because there could be entanglement between B and E. The subject of the entropy of E that gives you kind of a lower bound on the entanglement between B and E. But it's not rigorous, and I don't think it's visualized. Yeah. Well, a good thing about this coherent information is that it's monotonic on the quantum channels. So you can show that if there's a recovery channel, that's how you study this capacity. You ask whether there's the recovery channel to like a recovery channel such that gives you a system A such that remains the entanglement between A and the reference system. And because it's a coherent information is monotonic, then it shows that if you have like a perfect this bounded how much entanglement between A and the reference is. Yeah. And that's basically how you prove this theorem. First you prove that because the monotonic is a lower bound on the channel capacity, then you show that generically you can saturate this channel capacity by saturating the function. So yeah, okay, I think I'm skipping some. So now we want to apply this theorem to study the coherent information of the Chernobyl wormhole protocol. So first let's define. So here I have some labels: A reference, U, B, and P. So what are those labels in this House diagram? So one way to think about it is the following. So first we have an initial state which is A, and the reference together is a pure state. So you should think about initially the A describes the sum of your double states. It's a left union right. Yeah. In this wormhole protocol, we have a left system, left, and right system. For the two boundaries of the black hole, and we want to send some signal to. So we also have some reference. So initially we have the system A contains both the left black hole and the right black hole, and it's entangled with some reference system. So, and then this unitary that's described by this basically by this double shift deformation. So it's e to the I g v of t. So this v of t corresponding to, we start with a state and do a boost and acting on this operator and boost that. And then the environment, because we are tracing out some part of it, we view the E as a right black hole. And then the B is a left black hole. Okay. So that's how we identify this wormhole at the channel. So first we think about there's a so first we have some signal sending in, and we view the state at equal to 0 side or boosted. Is the left and right system as a whole system A, and then this signal is entangled with some reference system. Okay, and then what we are doing, we're acting on a unitary that acts on the two sides. The unitary corresponding to, we first do a time evolution forward and backward. So it's e to the minus I h r t tensor e to the I h left t, and then x with a unitary or left or right, and that's what I call as e to the I g v of t. Well, you can ask, yeah, maybe to complete the final part does not matter. R T is minus I L. Okay. And our initial state in this reference union A, the initial state is a PFD state with acting on phi R operator with some internal index I and tensor with some reference state, which we assume is a spin system, a qubit system with a state labeled by I. So that's our initial state. So we're asking, given such an initial state in the and maximize all the possible way of initial states, and we ask when we're acting on this unitary and trace out to the right-hand side, how big information that can be transferred to the left-hand side. Okay. So first, are there any questions at this point? So if not, then we can let me just move on. So we want to ask, what is the maximum? First, let's consider the one-shot protein transformation. So n equal to 1. Okay, that's not enough. So I will need 10 minutes. Okay. So first, yeah. right, right, right. And the unit phase. So you can build this. Yeah, here I'm using right now if you as a summation operator, but you can upgrade it to a unit phase. So it's maybe e to the I epsilon. Okay. Yeah. So we want to maximize over the coherence information. So it's the entropy of the left minus entropy of the right. Okay. So how do we do such a calculation? Here we do everything, and so we have some left and right. So the way to do that is first you need to use a quantum extreme circuits. Something that a project that is something I didn't explain, but talk to me afterwards. So basically, you can use a generalization of Ricci-Technologic formula to calculate the entropy on the left black hole and the entropy of the right black hole. That translates into the calculated entropy of the generalized entropy of the entanglement wedge for the left system, and the generalized entropy of the entanglement wedge of the right system. So this as that. In terms of give you a generalized entropy of the left region, that is given by this Bekenstein-Hawking entropy piece, area over 4G, plus the QFT entropy on the left region. And similarly, SR equal to the QFT on the right region. Okay. So you see something interesting happens when you look at the difference. This area piece cancels. And that is expected because we expect the area piece describes the UV entanglement between the two systems, and that doesn't contribute some IR entanglement between the reference and the left. So this cancels, and good. Nice. So we want that becomes a maximization of the bulk coherent information. Okay. And for the bulk part, then we will use Bekenstein bound for matter entropy. The Bekenstein bound tells you that for QFT, its entropy is less than equal to the energy times some temperature, some units. This bound was proven by Cassini used relative entropy. This basically is a rewriting of the relative entropy. So we have two inequalities for the matter part of the entropy. And so now if we look at that, these two inequalities, then you'll find you cannot substitute it in and to find the maximum because one of the inequalities is wrong. But it turns out that for the relative case, we are interested in which is you have the energy increase on the left is bigger than energy increase on the right. You'll find that this inequality is always saturated. That's beta. And therefore, for the case where for the relevant case, we can always this inequality always saturates, so you can always use this Bekenstein bound to bound this coherent information by the energy difference between the left system and the right system. And this energy difference is nothing but the boost energy. Remember, well, the boost operator is h right minus h left. So h left minus h right. Okay. And and we will later argue that this is, you can show that this one can always be saturated, And that gives you the one-shot quantum channel capacity, the maximum value of the boost energy. And because then you can generalize this discussion to the NCOP case to consider the regularized coherent information. You also find it bound, but because this energy is additive quantity, so it's actually extensive in terms of n. So you by that you actually find that this one-shot channel capacity saturates to the actual channel capacity, and then you can go and calculate the expected value of the boost energy in this system. What you find is that this boost energy is given by something called the O torque, and more precisely, it's a derivative of the O torque. I think I'm not explaining this clearly based on the time constraint. But anyway, there's some calculation you can do, and you'll find the concrete formula for the channel capacity. I have some comments with operator size winding and how this coherent information behaves under generic errors related to error correction, but I think I'll stop here. And oh, yeah.
Okay, thanks, the speaker. Any questions from the audience?
Thanks for the talks. About the hidden principle, what I know is it is a toy model used to solve the information paradox, and in that case, we treat so in this picture A as the initial black hole, E as the evacuate black hole, and B as the Hawking radiation. So if you throw the information into the black hole, you connect it from the Hawking radiation. And in this wormhole picture, you just said that B and E are just the left-hand side and right-hand side black holes. Could you just remind me, is there any similarity or differences
between?
Yeah,
you can. Yeah. So you can view this left-hand side as the early Hawking radiation, and the right-hand side as the old black hole. Yeah, okay. And then this protocol is like, if you have a, so this initial information was behind the black horizon, and this just tell you if you have with one more Hawking quantum. That's what gives by measuring the all right operator, you can extract it.
Thank you.
Other questions? Okay.
Just a very quick question. Can you explain a little bit what essentially in this protocol to make that boost energy is positive?
This boost energy is not necessarily positive, so it's a special feature. So
sorry, what I mean is you want the left side energy to be larger than the right side energy.
Yeah,
what's the reason for this essentially?
Essentially because you want this particle to move to the another side. So this presence of this particle gives you some excess of energy on the left-hand side compared to the right-hand side. So initially, this particle was living in the right-hand side, so the energy on the right is bigger than energy on the left. But when this successfully works, then you have the energy on the left-hand side, and that's bigger. And that's also the reason why this Bekenstein bond is saturated for the right side. Since you have asked, maybe I just say this formula, but maybe I can explain in 1 minute how to this formula related to my initial question is how this wormhole channel behaves. So I've argued that this quantum channel capacity is given by the derivative of O torque, and so the first feature is that it's proportional to G. So that tells you, and remember the G is the coupling constant of the double chip deformation. So it tells you the larger this coupling, the bigger the channel, and that could be larger than like other one value. And second, it's derivative to the derivative of some quantity called the O torque, And if you plug this derivative, you'll find that it's some behavior have a peak at scrambling time, which is log 1 over g Newton. So that's also a feature that the signal only sends through the wormhole successfully, or majority part of sends successfully at the scrambling time. And this derivation actually works for not only for gravitational system, it even works for with stringing correction. So that's the case where you do not scramble the system very well. And in that case, you find that the peak getting smaller. And so that's also a good thing because it tells you that when you have a maximal Lyapunov exponent, a maximal chaos, the channel works the best. When you have like a weakly interacting system, this scrambling or many-body teleportation does not work very well. Okay, that's a few comments.
Okay. Let's the second speaker again. Okay.